welcome to another AQA AS chemistry video. Today I'm going to be doing a video on increasing rates. This follows after the Maxwell-Boltzmann distribution video, and yeah, I'm going to go straight into it. So this is the last topic on energetics. I was planning on doing, so not energetics, kinetics. I was planning on doing a video on doing questions on this, but then I realized that I've kind of gone through those on a similar question on the previous papers. And I could go and do energetic questions if people really want that, but yeah, the questions are quite basic. I mean, they're very similar to the ones that are like kind of me explaining the diagram, but I guess I could do a video on that. I'm gonna go straight into the next topic though, and then I'll make the video on that. But anyway, let's get straight into it. There are many chemical reactions that we would like to go faster. For example, the Haber process, and many that we would like to go slower. So, preventing an explosion. The main methods for changing the reaction rates are changing temperature. So just to clear this part up, right? When we're looking at the Maxwell-Boltzmann distribution, when we're looking at exothermic, endothermic, and that's going to kind of lead on to the next topic, which is going to be on. I forgot what the next topic's going to be on. Well, let's just tell Leschatelier's principle, wherever that's equilibrium. That's it. We want to increase the rates of reactions, but at the same time we don't want to decrease our yields. We don't want to lead to an explosion. So that's why we take all these things into consideration. If you've ever thought, why does all of this matter? And yes, that's pretty much it, right? So I'm gonna shut up and I'm gonna actually go explain the video. So the main methods for changing reaction rates are changing the temperature. So earlier we saw the effects of heating on the Maxwell-Boltzmann distribution of energies. It raises the average energy but lowers the peak on the graph. So remember in the previous video I showed you the Maxwell-Boltzmann distribution. When you increase the temperature, the peak that peak gets lowered, and that's just to mostly accommodate for the fact that there's a more broader spectrum now of particles of a specific energy, and also to make sure that you understand the fact that the area underneath the graph represents the number of molecules, and that always has to remain constant. But it's also to take into consideration the fact that it shifts right because more particles, the most likely energy of the particle has increased. So the most likely energy of the particle has increased now because the temperature has also increased. So that particle, there's more particles that have a higher kinetic energy. So this gives more molecules energy greater than or equal to the activation energy, as I said before, and this means that more collisions will have the energy to react, so the rate increases. Right? If this still isn't clear to you, just watch my previous video. So heating the mixture also increases the number of collisions. So heating increases rates through two pathways. Increasing the kinetic energy, which means that more particles have the activation energy to successfully collide and react. Also, it increases the number of collisions per second as well. So, because they have more kinetic energy, so they're more likely to move and collide with one another. So, changing concentration. So, in solution, the majority of collisions of solid particle experiences will be with water. So we want more of these collisions to be with other reactants, as then the rate will increase. So by increasing the concentration of the solution, we increase the number of collisions that happen between reactants, and this doesn't necessarily mean there'll be more successful collisions, but it can mean that there'll be. It can mean more successful collisions, but not a substantial number of successful collisions. The reason for that is that there may be more collisions, but they may not be. I wouldn't call all of them successful collisions because they can collide, but if they don't have what I said in the previous video, if they don't have the activation energy to successfully collide, then they can collide, but there won't be any reaction occurring. But there will be a small increase in the rate of the reaction. The next one is changing the pressure. So in a gas, the molecules are far apart. So in this previous video, if I said before, the only thing that can increase that graph, right, or cause the graph to increase is if you change the concentration or you add more of your compound, right? So more of your reactant. So increasing your solid, your reactant would cause more collisions per second, that's pretty much what I was going through there. Changing pressure. So in a gas, the molecules are far apart, and consider the ideal gas law, PV equals nRT. Did I go through a video of that? I'm pretty sure I did. But increasing pressure reduces the volume of the gas. Makes perfect sense, because if that means that P would be equal to nRT over V. If you have a high pressure, that means your denominator here would have to be lower, or at least significantly lower compared to your numerator here. So in order to have a higher pressure, so increasing the pressure would reduce the volume of the gases, and this means that the molecules are closer together. If the molecules are closer together, they will collide more often. Think of this as like being on the bus in rush hour, right? The closer everyone is, the more you bump into people, and that's the same principle here. The closer the less space that these reactants have to move around, the more likely they are to collide with one another. So that's what that would that means there'll be more successful collisions, and the rate would increase. Now, catalysis. So a catalyst, I kind of went through this in the previous video, but a catalyst helps to increase the reaction rate by offering an alternative reaction pathway. The rate is higher because the new pathway has a lower activation energy. So the particles don't, nothing, if you look at the back, if I said in the previous video, if you look at the Maxwell-Boltzmann distribution, the Maxwell-Boltzmann distribution is exactly the same. It hasn't gone up or increased. It's like the reactions is still the same temperature, but it's just that the activation energy is less now because the reaction is occurring under a lower activation energy. So if that's the case, the graph may stay the same, but the activation energy is moved to the left, so there's now more particles that have energy greater than or equal to the activation energy. So more of those particles would successfully collide and react, and that would increase the rate of reaction. So as I said, a greater proportion of the molecules will have energy greater than or equal to, should say, than the activation energy, so there'll be more successful collisions. So if I was to explain catalysis, right, this is a very basic explanation. You'll get more into when you study year 2 chemistry or inorganic chemistry, when you're looking at transition metals, because they're the most likely catalysts that you understand. And even then, this is a very basic one, but I'll explain right. So what's going on here? So this is an enthalpy profile diagram, and I'll show you Maxwell-Boltzmann distribution. Sorry, enthalpy profile diagrams and the Maxwell-Boltzmann distribution can be used to explain how catalysts work, right? So enthalpy. So here you can see both reaction pathways. So this is I think you can clearly see which one is. If you want to really pause the video now and try and answer this, but which one is which one of these reactions is the uncatalyzed reaction, and which one of these is the catalyzed reaction? All right, you can pause the video now and try and answer that, but I think it's pretty obvious to see that this blue one here is the uncatalyzed reaction. If you didn't get that, if you didn't get that, the only thing you need to really remember is, why is one of these bigger than the other one? If this is the enthalpy, this is the progress of a reaction, which is just the time, right? It's just knowing that an uncatalyzed reaction will always have a higher activation energy. If you know that this from here, from the reactants to maximum peak, right, is the activation energy. If this is higher than this reaction, whichever one is going to be higher is going to be the uncatalyzed reaction, because a catalyst always has a lower activation energy, or allows the reaction to occur with a lower activation energy. But this here is just explaining how catalyst actually works. I should stop talking now and just go through the notes here. So the catalytic pathway has a lower activation energy, as obviously seen. So that's the catalyzed reaction. The Maxwell-Boltzmann graph. So here you can see the different reactivation energies for each pathway. Some molecules can use the old pathway, some molecules can use the new pathway, but not the old pathway, and some molecules can't use any. Overall, the catalytic pathway can be used by more molecules, so more molecules have enough energy to react via the catalyzed pathway. So not all particles will go through the catalyzed pathway. Particles will choose whatever pathway that they want to choose, right? but they're more likely to choose the catalyzed pathway because it requires less energy. The energy requirement for this reaction is much less. Think of it as a think of it like a if you want to, like a cost, right? If this is you wanted to buy something, right, and you wanted to buy something for the same price, you pick. Some people will choose to have the expensive version, and some people will, but the majority of people are going to choose the cheaper version, right? And that's what it is here. Like there's more. There'll be some that could choose the uncatalyzed reaction pathway, but the majority will choose the catalyzed reaction pathway because it's lower energy. It's a lower energy requirement for it to undergo in this reaction to get to the same point. This is what catalyzed reactions look like. I know in GCSE they just show you one. That's when it shows you as one kind of hump, right? That goes like that. It's just that's the mean. That's the average version of this. Even this is an average, right? There's actually loads of is actually more like this. It's still lower activation energy than the uncatalyzed reaction pathway, but it's still but there's just multiple steps, and it just depends on the amount of steps. But let's just say for the sake of this, right, it's just two. It's just two reactions that have a lower activation energy than the uncatalyzed reaction pathway. So overall, the catalytic pathway can be used by more particles. Already gone through that part. Anyway. All right, we're going to the next part now. So this part here is it's now the final part. I'm just going to talk about. It's the Max Boltzmann distribution graph, but it's not exactly as you show. It's got probability on this side and number of molecules in log base 10 of number of molecules in log base 10. Which one is the catalytic pathway and which one is the or uncatalyzed pathway? Pause the video now and try to answer that. Alright, so I think it's pretty obvious, right? But it's the catalytic pathway is this one. And the uncatalyzed pathway is this one. This isn't the same if the Maxwell Boltzmann graph because it's got the enthalpy here, but it's talking about the probability, right? And the probability that up until this point, there's a higher probability that the number of molecules will be going in the catalytic pathway, and there's the lower probability that there'll be with the uncatalyzed pathway. There's a low probability that they will there'll be like, as you can, the graph kind of thins off here. There's less particles that are going under this catalytic pathway because the enthalpy change will be there. But there's more particles here, as you can clearly see, because that's the majority of them. Those will be the catalytic pathway, because it's lower energy. It's just me repeating, regurgitating what's going on before. The majority of the particles will follow this pathway. And that's it. So, the final part of this is going over, so just kind of reviewing or summarizing this video. Ooh. So, reaction pathway, right? Got the catalyzed and an uncatalyzed pathway. The catalyzed pathway has a lower activation energy, and that means that more molecules will successfully collide. But with the uncatalyzed pathway, it's just vice versa, really. Where there'll be a higher activation energy compared to the compared to the catalyzed pathway. It's higher activation energy. and then there'll be less molecules that will successfully collide. And that's it. So thanks for watching this video, and that's it. Ooh, successfully collide.